Okay, can you see the slide? Can you hear me?
Yeah.
Can you see the slide?
Yes.
Yes,
Okay,
we can
good.
see.
So yeah, hello everybody. Also like to thank first Jan and David for setting this up. It's quite an interesting event. So I'll be talking about the thermodynamic uncertainty relation and highlight a few aspects. So this is work which started with Andre Barato, who is now faculty in Houston, Patrick Pizzonka, who is now postdoc in Cambridge, did a PhD on this, and my current postdoc grad student is Timo Kuyuk. And I'll show you very recent results we got together towards the end. Okay, so with this slide, you know, many of you have seen that before, but I want to highlight the basic idea of stochastic thermodynamics. By the way, do you see this gray rectangle? Can you see that when I highlight something?
Yes, we do.
Thanks, David, thanks. Okay, so as you know, the basic idea was to explore what are the rules which have been developed in the 19th century to understand steam engines, whether and how these rules can be applied to molecular motors. They were just mentioned. This is the F1 ATPAs, and we can do single molecule experiments. We see single traces, we see fluctuations. And then one of the questions is, for instance, how efficient are these molecules? And as I will show you, the thermodynamic uncertainty relation will give a quite surprising insight into the efficiency of such motors, of real motors, not about toy models, but real systems, real experimental data. But I want to start with the original question which brought me into this. So my original question was, suppose you want to measure time and you want to measure it with this kind of clock. You have to appreciate that we do this in a finite temperature environment. So obviously there will be fluctuations and it will be impossible to have an infinitely precise clock. It will also always come with some error. And my question was kind of naive and simple, you know, is there a relation between the precision of such a watch and the cost of running it? I mean, all these watches have batteries, they are draining power. So the naive question that originally 6 years ago was whether there is a relation between the precision and the cost. And as you all know, today we know the answer. So at 300K, if you want to measure, let's say, 1 day with a precision of 1 second, it will cost you at least 10 to the minus 11 joule during this day. Okay, and if you see that for the first time, that's obviously a kind of intriguing figure. And of course, as you know, it's a result of this thermodynamic uncertainty relation. So these introductory slides, I apologize to the experts, but I realized that the audience is kind of broad. So this is for the people who are a little bit further away. So when I asked this question, I mean, obviously you start with a simple model. So and this is where Andre came in and later. This is my simple clock. So the hands of a clock, the big hand or the small hand, they are moving to the right. This is here now mapped to some linear motion. And they go preferentially to the right, but there is a finite rate of going backwards. K plus is the forward rate, K minus is the backward rate. And then we all know that after time t, there is a net advance of K plus minus K minus times t steps. But this will not be precise. It will come with an error, it will come with a variance, which is given by the sum of the two rates. And then we can define the uncertainty as the variance divided by the mean squared. Mean is called output here, and you get this relation. This is about the output, about the error, but there is a cost to it. And for the simple model, we know from stochastic thermodynamics that the cost is given by the log ratio of the rates. sigma, the red sigma is the entropy production. And typically we write this asymmetry in the rates as an affinity. And in the example which was just discussed, this would be the delta mu of the ATP hydrolysis. So if you need for one step to the right, you need one ATP, then this would be the 25 kBT we're just talking about. Okay, these are all trivial relations, but then you have to put them together and you find that the product between cost and uncertainty is this hyperbolic function of the affinity, and that can be bounded by 2 kBT. And that's independent of the runtime. Okay, so this was historically the kind of first surprise that there is this nice relation. Now, obviously, this would just be a peculiarity of this particular model. So the question was whether that holds more generally. So the idea is you could say, okay, this is certainly a bad watch, but we need some error correction, we need some feedback. Swiss watches are much more elaborate. So we were starting looking at more complicated wired watches. And it turned out numerically and in a lot of limiting cases that this red box, this relation between cost and precision holds universally. And when we put that out as a conjecture supported by lots of numerics, Todd Gingrich and Jordan Horowitz and the two more collaborators proved it, as most of you know, in 2016, going through large deviation theory. Okay, so if you have a process which is supposed to be 1% precise, you'll pay at least 20,000 kBT. And if you want to measure 1 day with the precision of 1 second, you get a 6 to the 10 to the minus 11 joule I mentioned at the very beginning. So I should stress, this is the inevitable universal cost, and it's based here on assuming an autonomous stationary Markov process. And we had that before during these days. You can rephrase it as a relation between the entropy production, the mean of any current. This is important, you can take any current, and dJ is the dispersion of the current or the diffusion coefficient of this current. Okay, now it's a nice relation, but I now want to show you what you can do with it in the real world. And this is one of the examples I still like most. You can use it as a tool for thermodynamic inference. So let me move to this. So here is the experiment. This single molecule experiments, these are data from Stephen Bloch's lab. So what do? You have a molecular motor which is moving along this microtubule. The motor is here, it's a tiny motor. Attached to the motor is a bead, and this bead can be controlled in this laser trap. So you can apply a constant force on the motor. The motor is running to the right against this force, which you can imagine as a weight pulling to the left. And then the experimental data which you get are the velocity of the motor. You get the dispersion in the velocity, which is the diffusion constant. And this is typically combined into what is called a randomness parameter. And when you plot that randomness parameter as a function of the ATP concentration, you get data like this. And these are for 3 different forces. These are forces in the piconewton range. Or you can do it as a function of the applied force at a constant ATP concentration. So these are data which have been around for 20 years or so. And I'll now show you that using this data, you can infer a bound on the efficiency of the molecular motor. And we just had a discussion on the efficiency of these systems. Okay, so that's what we did here. And as I said, this is still the example I like most. So what is efficiency? Efficiency is the ratio between the output and the input. The output for molecular motor, if it runs against the force, is force times velocity. The input is ATP, but you don't know how much ATP the molecular motor needs, how much it hydrolyzes. You can't see the single molecules vanishing. But we know that there is an entropy production, which is the input minus the output. So that's what's lost. So we can replace the unknown input by the sum of entropy production and output. That's what we're doing here. And then we have a relation, we can express the efficiency by the velocity and the entropy production. And for the entropy production, we have the uncertainty relation. So you plug that in and you get an upper bound on the efficiency, which involves only experimentally measured quantities: the velocity, the diffusion coefficient, the applied force, and the temperature. So I'm plotting this function here in this over this experimental data. So here was the randomness, here was the load, the applied force, and the colored curves are curves of constant upper bound. So let's take this data point here. So it may be hard to see, but this is 45%. So at this data point, which means at this applied force and this measured randomness, our theory tells us the efficiency at this particular point is less or equal to 45%. Okay, and this is a really interesting statement because it's totally model-free. We do not assume any specific chemomechanical cycle. And this is the first time someone can make a statement of this sort. I mean, there are various calculations for the efficiency of molecular motors, but then you always put in some model. And here, for the first time, we get an upper bound. It doesn't mean that the motor is 45% efficient. It could be less, perhaps 35%, perhaps only 2%, but it's definitely not more than 45%. Okay, and I really want to stress this universality of this result, the independence of any assumption on how chemical energy is transformed into mechanical work. Okay, let me highlight one more result, which was already mentioned by Takahiro in his introduction. And that is this issue of whether it's possible to reach Carnot efficiency at finite power. And for me, this was brought up in a very nice PRL by Benenti and Casati and Keiji, where they speculated that with a magnetic field, one could have finite power at Carnot efficiency. So this started a whole industry. I don't want to go into this, but I want to show you what the uncertainty relation implies on this question. So if we have a heat engine like this, so we take heat from a hot bath, we put it into a cold bath, but the main purpose is to get out some work. And if we run it in steady state conditions, then we can apply the thermodynamic uncertainty relation to the work current, for instance. And when you combine this with the first law, then it's a matter of 3 lines to get this relation here. So the statement is that the work current, which is the power, is less than a product which involves the difference in efficiency to the upper limit, which is Carnot. So typically, if you just look at P less than eta C minus eta, this means that the power vanishes linearly as you approach Carnot. But there is an amplitude in a sense, and this amplitude is the diffusion coefficient for work, for power. So this offers a loophole. You can, if the efficiency vanishes, but if at the same time the fluctuations blow up, you could have a situation that the product is finite. So in principle, you could reach Carnot at finite power, but only at the price of having divergent power fluctuations. And this insight unified quite a number of case studies. Massimiliano had a paper, Michele had a paper, and I think it's a nice universal relation which helps us to understand this issue. Yes, in principle, it's possible to reach Carnot at finite power, but certainly only at the price of having divergent fluctuations, which then finally leads to a trade-off, not involving only power and efficiency, but also constancy. And this again is something which people have observed earlier in special cases. Okay, so for me, these kind of two results, the efficiency of the motor and the insight we get into this issue of reaching Carnot at finite power, or by the way, any other upper limit for efficiency for isothermal engines like molecular motors, it would be reaching efficiency 1. And again, that would be possible only if the power fluctuations diverged. Okay, so much to establish results. And in the final part, I want to advertise very recent results where we were able to generalize this uncertainty relation to time-dependent driving, starting with arbitrary initial conditions. So this is a particular generalization, but I think it's what should be really called a generalization, because as you will see, it simplifies to the established relation if we specialize, for instance, to non-equilibrium steady state. So how does it work? We assume some Markov network with rates, but the rates are not constant. They rather depend on a driving protocol. So they depend on a control parameter lambda, and this lambda parameter has some functional dependence on time. And the key point is that we write this as a function of a speed parameter v times t. So we imagine the experimentalist has a knob and he or she can turn this knob faster or slower. But we are not assuming a particular protocol. It doesn't have to be periodic, it could be anything. But we want to write it in this form that it depends on a speed parameter, which basically is a little bit like scaling time. And then we observe the system for a time, capital T. We will have a mean current, which depends on the observation time, and it depends on that speed parameter. And then the new relation is this box. So you see on the left-hand side, an additional term, delta J. Without the delta J, it would be the ordinary uncertainty relation. So what is delta J? Delta is an operator which is the derivative with respect to the observation time and the derivative with respect to the speed parameter. So you measure the mean current over a certain time, and then you look at how does that mean current vary with time and how does it vary with that speed parameter. So these are, and I'm stressing this because that's crucial, these are operationally accessible quantities. And then the statement is that if you combine these quantities in this way, we get a truly generalized uncertainty relation for arbitrary time dependence of the driving and an arbitrary initial state. So let me show you two examples. So here we do the presumably most simplest case. So we take a harmonic trap, and we have it at rest initially, some initial state, and then we start pulling it with a velocity v for a time t. And then we use this relation, and we can take any current. So we can do it for just the velocity, which basically means we measure the distance over which the particle has traveled divided by the time. This is the finite time velocity, and then we look how does that vary with time and with v. And I'm now plotting the quality of this bound by plotting the ratio between the left hand and the right hand side. This is the quality factor. And the full lines here, the full lines is the bound based on just measuring the displacement of the particle. And you see for short times, you get about 80%. We could take another current, and for instance, we can take just the power. And these are the dashed lines as a function of the observation time. And there you see the bound gets better and better the longer we observe. But let me come back to this short time result. So it's quite interesting that you get about 80% of the entropy production by just looking at the displacement of your bead. And there is no need to know the stiffness. You don't need to know how stiff the trap is. The trap could be very soft. It could be very steep. You don't need additional input. You just do the experiment. You look how the mean current or the mean displacement in this case changes as a function of time or as a function of velocity, and you get an estimate on the entropy production during this process. This was for currents. Let me show you another example where we were able to generalize this to what we call state observables. So these are, in a sense, time-symmetric observables. And let me explain it by just using a two-state system. So here is a system. We have two states. Each state has an energy, and we make the energy dependent of a protocol. So the energy as a function of time is some 1, 2, is some function, and this function involves a speed parameter. So for instance, this could be something like this, and when we do it faster, it will be this, or when we do it slower, it will look like this. Okay, so this is the speed parameter. And as an observable, we just ask, is the system at the final time in state 2? And for this observable, we have here the boxed uncertainty relation. So x is this observable. Delta of x is again the mean value of the observable, or the dependence of this mean value on the observation time and on the speed of running the system. And the uncertainty relation is just given by this delta x squared divided by the dispersion. That's less than the entropy production. So as I said, we can use this observable at the final time, but we can also use an observable where we just count the total time spent in state 2 during that driving protocol, during this process. And the relation holds for both types of observables. So I find it surprising that you get an estimate on entropy production by looking at, I mean, quite generally speaking, by looking at time-symmetric observables. And again, in the diagram, you find, or you see the quality of the bounds. We have compared here, for this simple case, 3 different observables. So the one we were talking, I was just mentioning, but we're also looking at a current observable, which is the red trace. This is just the current going from left to right, for instance, on average. Okay, and depending on the time of observation, one or the other or the third one of these bounds is best. But again, you see, you know, for instance, taking this observable at the final time, this is the blue curve, we can get here 85% of the total entropy production just by looking at whether or not the particle or the system is at the end in state 2. I mean, these are very simple experiments. They should be operationally easily accessible, and we get these kind of nice relations as a generalization of the original tour, which applied only to non-equilibrium steady states. Okay, I guess my time is over. So let me come to the conclusions. With this last result, we have generalized the tour to time-dependent driving, and I'm emphasizing this tightly generalized. What I mean is that when we specialize this relation to the simplified situation of non-equilibrium steady state, we indeed get back the original relation. So in that sense, it provides a real unification and extension. I don't think I have to go through this. Let me just mention as an aside, for those who like open problems, to my knowledge, it's still not proven for underdamped dynamics. And here are 2 papers, and I want to highlight the nice review by Jordan and Todd Gingrich on this uncertainty relation. Okay, so far from my side, I'm looking forward to your questions. Thanks.